Hey everyone, this is our lesson on electron configurations. So by the end of this lesson, you should be able to analyze an atom in terms of the location of the electrons. But before you get started, you may want to review Bohr and quantum mechanical models. So let's talk about our rules that we use to write an electron configuration. So first of all, an electron configuration itself is a way to write electrons in their orbitals and to know their location easier than having to draw a Bohr model out every time. And since we can't really draw out quantum mechanical models, this is the way that we will write those electrons. So first, we learn with what are called off-ball diagrams. And with those, we label the lines with our quantum mechanical orbitals. And we use arrows to denote electrons. And when we write these, and I know this kind of sounds weird, you don't know what the diagram looks like, I will show you one in a second. But when we write these, we follow 3 different principles or rules to help us write them correctly. So the first one is off-ball principle. And it states that you always start in the lowest energy level first, which means anytime for any element, when you write an electron configuration, you always start with 1s. I like to say this is the first rule to follow. It's called off-ball principle, and A is the first letter of the alphabet. So if that kind of helps you make that connection. The next one is the Pauli or Pauli exclusion principle, which states that each orbital can only hold 2 electrons, and those 2 electrons must have opposite spin. So that means on each line, you have to have an up arrow and a down arrow. Okay, that's what tells you the spin. And then the last rule is called Hund's rule, and this states that every degenerate orbital gets 1 electron before you fill it up. So a couple things with this one. The word degenerate here means equal energy. Okay, so those are your orbitals that have more than one shape. So like your P, D, and F orbital. So we'll focus on this one, especially with the P orbital. The P orbital gets 3 different shapes, which means it has 3 lines for a P orbital. And then what you do is you'll put 1 up arrow on each line before you go back and fill in with the down arrows. So I call this your babysitter rule. Most of you have probably experienced babysitting either a sibling or a relative, maybe someone like a neighbor, anything like that. You've probably watched kids before. Maybe you work at a daycare or child care facility, something like that. So when it's snack time and you're watching more than one kid at a time, you have to give each kid a snack before you can go back and give a kid a second snack, right? That's only fair. You have to give each one a snack before you can go back and give them a second snack. That's what you're doing here. You have to give each orbital an electron before going back and filling up. You can't pick favorites here. So again, this only applies to our P, D, and F orbitals. So this is what an off-ball diagram looks like. I know I have lines here. Some of them are noted by boxes. So first off, you see off-ball principle, because we start in 1s, Pauli exclusion, because each one gets a 1 up and 1 down, and then Hund's rule, because you put 1 in each of the boxes of 2p before you go back and fill up from there. So let me X out of the video here. Once you get to the 3D orbitals, it does change order a little bit, and this is all due to energy. So you will actually fill up your 4s before 3D because 3D is slightly more energy. So when you get to that point, you'll fill up 4s, then 3D, then 4p because it kind of fits in the middle. And when we're in class working in group activities, things like that, I will go over how that looks on the periodic table. So now let's try an example here. So we're going to write the electron diagram for chlorine. Okay. First, you have to count up all the electrons. So we're dealing with all of them, not just the valence. And chlorine has 17. Then you're going to follow the rules on the previous slide, starting with off-ball principle. So when you do that, you have 1s, and I will say you can either see them drawn upward like we did on the last little animation, or you'll see them drawn sideways just to save space. So we have our 1s orbital, should have an up and down arrow, 2s orbital, up and down arrow, 3p, these should be separated in 3 separate ones. I'm sorry, 2p, and we put 1 in each, going up, then filling back in, going down. So that's 2, 4, 6, 8, 10 of my 17. So I have 7 left. When we fill up 2p, we go to 3s, and that should make sense because n equals 1 only has a 1s, n equals 2 has a 2s and 2p. Then you go to n equals 3. So n equals 3, we're going to start with 3s, 1 up, 1 down. 3p, at this point we only have 5 electrons left. So you're going to put 1 up in each first, then go back and fill up with what you have left, which would only be 2. And if you run out, you run out. You can't fix that. So this is exactly what the 3p would look like for chlorine. So this matches the numbers that we learned in the Bohr model lesson with how many electrons can be on each orbital. Because if you look, 1s, like n equals 1 could only hold 2. N equals 2 could hold 8. And in the s you have 2, and in the p you have 6. So 2 plus 6 is 8. Okay. So I want you to pause the video and try to draw the electron diagram for aluminum. All right, so now that we've talked about the diagrams, we can talk about the shorthand that you will use more often. So first off, we have regular shorthand, which is where the number of arrows on an orbital actually becomes a superscript or an exponent on that orbital. So if you have 2 electrons in the 1s, you would have 1s with a 2 superscript or exponent. So hydrogen only has 1 electron. So it would go in the 1s, and it would be 1s1. Now, when you say these out loud, like if we go over any examples in class, you would say 1s1. You don't say 1s to the first or 1s squared or 2p cubed. You would say 1s1, and I would know that second number is an exponent. Then the other type of shorthand that we have is the noble gas shorthand. And this one you will need your periodic table for. So you find the element that you want to write the configuration for on the periodic table, put your finger on it. Then you're going to go up 1 block. Then you go all the way to the right to your noble gas, because that's going to be your group 8A. You're going to put that noble gas in brackets. The configuration of the noble gas and the desired element will match up to a P6. So a 2p6, 3p6, 4p6, whatever it would be. So you actually get to use your substitution property from math to substitute in the noble gas portion, or the noble gas for that portion that matches between the 2 configurations. And we'll see this in an example in a second. So here, again, let me get rid of my video. So for noble gas configurations, if we find sodium on the periodic table, you go up 1 block all the way over to the right, you're going to hit neon. And if you look at these configurations, so let me change pins here. If you look at these configurations, for neon it goes to a 2p6, and you actually match all the way up to 2p6 for sodium. So since these match, you can actually substitute in your noble gas for that 1s2, 2s2, 2p6. Then all you have to write is what was left, what was different between the 2 configurations. So it would be Ne 3s1. So now I'm not going to cut my video on, so we'll see this box at the bottom. We're going to write the regular shorthand for oxygen. So again, you start by counting up your electrons. Oxygen has 8. Recount how many electrons go in each orbital and write them as a superscript until you run out. So when you do that, you've got 1s. 1s can hold 2, so we're going to put 2. Then you've got 2s. 2s can hold 2, so we're going to put a 2. We've used 4 of our 8 here, so we only have 4 left. 2p can hold up to 6, so we're going to put all 4 in that 2p. So we've got 1s2, 2s2, 2p, 4. So now I want you to try to write the noble gas configuration for oxygen as well. So now let's talk about configuration exceptions. There's only a couple here that we need to know. And this is specific to the d orbital for us. It does also happen with the f orbital, but you guys won't have to go into writing configurations for those. So atoms with the d orbital will want it to be either full or half full by the end of the configuration. So if we can have a D5 or a D10, we want it. If you have a D3, you can't do anything about that. A D7, can't do anything about that. But if we can get to a D5 or a D10, we want that. So now we're looking at one electron from the previous s orbital that you're looking at. So we've got, like 4s, 3d, 4p. So we're going to look at that 4s, and you're actually going to promote one electron from that s orbital into your d orbital to stabilize it. Because if you promote one electron, now your s orbital is half full, and then your d orbital will also be full or half full. So one of the examples here, and you can star these on your periodic table, the column in your transition metals that start with chromium and copper. Those are the two columns to know that follow this rule. So if you were to write the configuration just off the cuff for chromium, it's got 24 electrons, and it would fill all the way up to 4s2 3d4. Well, that 3d4 makes us very unhappy. We want to be a d5 or a d10 if we can. So what you actually will do is promote one from this 4s. So we're going to mark that out, promote it up here to make it 4s1 3d5. That's what we want. Again, also does the same thing with copper. Now let's talk about ions. So ions have to end on a P6 as well. So these need to look like a noble gas configuration, because the whole point of an ion is to gain or lose electrons to look like a noble gas, to be stable like a noble gas. So that's what we're doing here. So cations will lose electrons in the s or the p orbital to go down a shell to a full octet. Anions will add electrons to their outer orbital in that p shape to fill up that orbital. So for example, magnesium 2+. So up here is your charge, 2+. Magnesium normally has 12 electrons, but that 2+ means we lost 2 electrons, so now we have 10. So we're going to fill this up, and as you can tell, when you fill this up, we end on a P6. That's what we want, because otherwise this would have been 1s2, 2s2, 2p6, 3s2, but we got rid of those 3s2 electrons. And here it just shows you losing that outer shell electron. We've dropped that orbital, and now we have 8 on the outer shell. So let's try this one. So remember, copper is one of our tricky ones. So we're going to write the electron configuration. Again, start by counting all your electrons. It's got 29. Fill up the orbitals following your rules. And then remember to check for full or half full d orbitals. So normally when you write this, it would be 4s2 3d9. We don't like that, so we promote one up from 4s to 4s1 3d10. So now I want you to write the electron configuration for F-, which is an ion. Remember, if it's a negative ion, it's gained electrons, and it's gained however many the number is there. So now after this lesson, I was a little bit longer, sorry, but after this lesson, you should be able to know the